In this video, we are going to talk about electronegativity and polarity, and determining if a molecule is polar or nonpolar. You might have noticed, if you've ever done anything in your life involving grease, that water doesn't clean up grease very well. Water and grease don't really mix together, just like water and oil don't mix together. And the reason for this is that water and oil, or water and grease, are essentially on opposite sides of the scale, so to speak, when it comes to polarity. Water is very polar, oil is very nonpolar. Because of this, water molecules, as it states here, are attracted to each other because things that are polar tend to stick together and things that are nonpolar tend to stick together. And they're not really interested in interacting with stuff that is the opposite of them. So the water and the oil kind of stay separated from each other because they like themselves, essentially. The reason for this is if we look at water for an example here. Water has this structure where we have an oxygen in the middle and two hydrogens bonded to it. This bond between the oxygen and the hydrogen is what's called a covalent bond because, again, these are all nonmetals. And in covalent bonds, if you remember, electrons are shared between the atoms participating in the bond. So the oxygen is sharing electrons with the hydrogen, and the hydrogen is sharing electrons with the oxygen. What we haven't talked about is if that sharing is completely equal. And the truth is that sometimes it is, and sometimes it's not. Sometimes they do not share those electrons equally. And the oxygen-hydrogen bond is an example of that. The oxygen has what we call a high electronegativity. And electronegativity is kind of a fancy way of saying it really likes electrons. It has a strong affinity for electrons. It will draw electrons to itself. Hydrogen doesn't necessarily have a really low electronegativity, but it is significantly lower than oxygen's. Oxygen's is relatively high. It's actually the second highest of anything on the periodic table. And so because of this, the oxygen, because it really wants electrons, it really likes electrons, it will essentially hold on to those electrons a little bit more than it should. It doesn't equally share the electrons with the hydrogen, and as a result, the electrons kind of stick around on the oxygen a little bit longer than they should. They're not staying on the oxygen 50% of the time, and on the hydrogen 50% of the time. They're staying over here with the oxygen a little bit more than 50% of the time, and we get what's called a dipole moment. Because the electrons are staying on this side of the bond a little bit longer than they should if it was being equally shared, you get a little bit of a negative charge built up over here, and then you are required then to have a little bit of positive charge over here. So the electrons stay on this side of the bond a little bit more, giving it a negative charge, and on this side you then get a deficit, essentially, of electrons, leaving you with a slight positive charge. And this is a slight charge. This is nowhere near a full charge. But just because it's a slight charge does not mean that it is insignificant. It's actually quite significant. So this, like I said there, this results in a dipole moment. Fancy way of saying slight charge difference between the two atoms. And this is what we would call a polar bond, where we have unequal sharing of electrons between the two atoms that are participating in the bond. Alright, so, like I mentioned before, the reason that the oxygen takes more than its fair share of the electrons is because it wants the electrons more, and the way we're going to quantitatively decide which atom wants electrons more is we're actually going to look at the electronegativity of an element. And those electronegativities can be found on a table like this. So there's lots of different designs, essentially, for these tables. This is the one from your book. And so you can see here that fluorine actually has the highest electronegativity of anything on the periodic table. It has an electronegativity of 4. Oxygen is the next highest after that. And you can see hydrogen over here. If you remember, I said it wasn't particularly low. It's a lot higher than any of the alkali metals or the alkaline earths, and even some of the non-metals and, well, I don't know, it's not quite higher. It's the same as phosphorus, so it's about the same as some of the lower non-metals, and it's higher than some of the metals down here as well. So it's not super low, but it's not really high either. The highest electronegativities are all going to be up here in the top right corner of the periodic table. Electronegativity tends to increase as you go to the right on the table and as you go up the table. Electronegativity increases. It is the same as ionization energy, if you remember from exam 2. So as you go to the right and as you go up, electronegativity increases. When we are looking at bonds in a molecule to try and determine if there is a polar or a non-polar bond, a slight difference in that electronegativity is actually not going to be enough for us to say that it is polar, because as you might have noticed, there's very few elements that have exactly the same electronegativity. There are some, like hydrogen, phosphorus, and tellurium, all have the same electronegativities, but for the most part they are different, at least by a little bit. And so just having any difference in electronegativity is not enough to make a bond polar. You have to have a significant difference in the electronegativity. So our cutoff for where a bond is considered polar versus being just covalent or pure covalent or non-polar, it's the same thing here. So non-polar would be the same as pure covalent. Our cutoff is 0.4. So if there is a difference between the two electronegativities of the atoms participating in the bond, and that difference is greater than 0.4, so this should really be 5 there, not 4. So 0.5 to 2, that difference would give us a polar bond. If the difference is 0.4 or less, that would be a nonpolar or purely covalent bond. If you have a really big difference, that means that you have a metal and nonmetal, which would just be ionic. But we're going to be focusing on these two here, not quite so much on that last one. So if it's greater than 0.4 difference, it doesn't have to be at 5, depending on what tables you look at. This particular table doesn't go down to the hundredths, but you can find electronegativity tables that go down to hundredths. If it's greater than 0.4, it is considered polar. And if it's 0.4 or less, the difference between the two atoms, that would be purely covalent. So if we look at an example here, and actually let me see, I forgot to write this one in here. So that will teach me to not look ahead before I make a video. So 10.10 says it wants us to determine if the bond formed between each of these pairs of atoms is purely covalent, polar covalent, or ionic. So we have 3 different options here. There is strontium and fluorine, nitrogen and chlorine, and nitrogen and oxygen. So why don't you go ahead and pause the video for just 1 second and try to figure out if these 2 atoms are bonded together, and we have 3 different possibilities here. Are each of those going to be purely covalent, which would be nonpolar, polar covalent, so it's a polar bond, or ionic? So go ahead and pause the video for a second. All right. So even without looking at the electronegativities, I can tell you this first one it's going to be ionic. And again, the reason I can do that, and I mentioned this in the previous slide, is that I have a metal and a nonmetal. But if I want to go ahead and double check that, strontium is 1, fluorine is 4. So if this is 1 and this is 4, that is a difference of 3, which would make it ionic, because our cutoff for that was if you get up to a difference of 2 or greater, that would be ionic. So this is an ionic molecule. The next one here, nitrogen, if we check the table, is 3. I believe it was bonded to chlorine. That is also 3. So if the two electronegativities are both 3, then the difference would be 0, which would make it a purely covalent or just nonpolar bond. So they are going to equally share the electrons between the two of them. They will not have the electrons more so on one side versus the other. For this one, on the other hand, so nitrogen is 3, and if you go back and check the table, oxygen is 3.5. Now the difference is equal to 0.5. And if we check, if we have a difference of 0.5, that is going to be a polar bond. So this would give us polar bonds, any bonds between nitrogen and oxygen. All right. Hopefully that was pretty clear. If not, we can talk about it some more when we get together and chat. But going ahead and moving on here, that particular example there was not actually showing us how to determine if we have a polar molecule. What we were determining in that example was, do we have polar bonds? That seems like it should be, well, isn't that the same thing? If we have polar bonds, shouldn't we also have polar molecules? And the answer is, most of the time, yes. But for quite a few situations, there's quite a few situations where you can have polar bonds and end up with a non-polar molecule. How that works is if, for example, we have a molecule like this, where we have a central atom and we have electrons being pulled in two directions that are exactly opposite to one another. So an example of this might be something like, actually let me make sure, yeah, okay. Make sure we're going to do this as an example in just a second, but CO2 looks like this. Carbon has an electronegativity of, actually it's 2.5, sorry, 2.5, and oxygen is 3.5. That is a difference of 1, and that is a polar bond. And so you're going to have electrons pulled towards this oxygen and towards that oxygen. So you have two polar bonds, but this molecule is actually nonpolar. Because the oxygens are exactly opposite to one another, they're pulling exactly the same strength, with exactly the same strength, in exactly the opposite direction, and they cancel each other out. So there's no overall movement of electron density one direction or another because they cancel each other out. So if we have polar bonds and those polar bonds are identical and everything attached to that central atom is the same, we're going to end up with a nonpolar molecule. So this is the same thing here. If we have 3 things attached to the central atom, they're all bonds, all exactly the same bond, then it's going to end up being nonpolar. But this is the only situation where that can happen. The only situation where you can have polar bonds and end up with a non-polar molecule is if the molecule is completely symmetrical, where everything attached to the central atom is the same, not just the same in terms of it's all bonds, I mean exactly the same. It is the exact same atom at each of these points. That is the only situation where that could happen. And that includes having lone pairs. So like right here, this particular molecule has a lone pair that's sitting right there, which is what's causing those bonds to be down like that. This is not a completely symmetric molecule. So it is only true for completely symmetric molecules where you can have polar bonds that are present, but the molecule ends up being nonpolar. All right. So a couple quick examples here of how this can be applied. And I'm sure we'll talk more about this determining if a molecule is polar or not when we get together and chat. We talked about water molecules and how they don't like oil, which then begs the question, if water doesn't like oil and oil doesn't really like water, how does soap work? Because soap seems to like both of them. Soap will clean up the oil, but soap will also get carried away by the water when you wash your hands. The reason for that is soap is actually this giant molecule. Water molecules and oil molecules are usually not all that large. The oil is definitely bigger than the water for sure, but it's usually not too large. Otherwise it turns into wax, essentially. But with soap molecules, you have a really large molecule where one end of the molecule is what we call a polar head, and the other part of the molecule is a long nonpolar tail. So you have usually an ionic group, actually, like a negatively charged group at the end here that is very, very polar because it has a full charge that is very polar, and then it's attached to this string of carbon and hydrogen that is nonpolar. And that string of carbon and hydrogen is what will grab the grease. So this end of the molecule will interact with the grease to carry it away, and then the water comes along, grabs that polar head group, and drags the whole group away. And so soap actually works because it essentially has both. It has a polar end of the molecule, and it has a nonpolar end of the molecule. And so it's able to interact with both kinds of molecules. All right, we'll call it there for this chapter. Make sure that you are working on the homework for this chapter as soon as possible while it's still fresh in your mind. And I will see you all in the next chapter.